For decades, Pluto was ignored, a cold shadow beyond Neptune. Too small, too far, too insignificant. We even took its planet status away. Then in 2015, a spacecraft raced past Pluto at 50,000 kilometers per hour. And what it found rewrote the story completely. Mountains of ice, flowing glaciers, a giant heart carved into the surface. Pluto wasn't dead, it was active. And the more we study it, the stranger it becomes. Because beneath that frozen shell, Pluto may still be changing. This is the world that refused to be simple. In the years since the New Horizons flyby, and with new data from powerful observatories like the James Webb Space Telescope, Pluto has transformed from a dismissed dwarf planet into one of the most fascinating worlds we've ever explored. Tonight, we're counting down the top 10 most important, up-to-date things we now know about Pluto. Discoveries that reveal a world still evolving, still surprising, and still hiding secrets beneath its frozen surface. Number 10. Pluto is geologically active right now. For decades, scientists believed Pluto should be geologically dead. It's small, it's cold, and it lost most of its internal heat billions of years ago, or so we thought. But when New Horizons arrived, it revealed something shocking. Pluto's surface shows very few impact craters in key regions, a telltale sign of recent resurfacing. In planetary terms, recent can mean tens of millions of years, not billions. This tells us Pluto is not a frozen fossil. It's a world that has been reshaped again and again long after its formation. Some areas are ancient, others are surprisingly young. Pluto is a patchwork planet, a mosaic of different ages and processes frozen in time. Number 9, Pluto has a living, breathing atmosphere. Pluto's atmosphere is incredibly thin, over 100,000 times thinner than Earth's, yet it is one of the most complex in the solar system. It's made mostly of nitrogen with traces of methane and carbon monoxide. But what makes it extraordinary is how it behaves. As Pluto travels along its long, elliptical orbit, parts of the surface warm just enough for nitrogen ice to sublimate, turning directly from solid to gas. When Pluto moves farther from the Sun, that same atmosphere freezes and falls back to the ground like snow. In recent years, data from the James Webb Space Telescope confirms something even stranger. Pluto's atmospheric haze actively cools the planet. Instead of trapping heat like Earth's atmosphere, Pluto's haze particles radiate heat back into space, a cooling system unlike anything else we've observed. Number 8. A climate cycle driven by ice, not water. Pluto doesn't have rain, it doesn't have oceans, and it doesn't have clouds made of water drifting across its sky. But make no mistake, Pluto has weather. It's just weather that follows rules completely unlike our own. On Earth, climate is shaped by water. It evaporates, condenses, falls as rain, freezes as snow, and flows back to the sea. But Pluto exists in a realm so cold that water ice is locked in place like stone, unable to sculpt the landscape. Instead, Pluto's climate is driven by substances we normally think of as gases: nitrogen, methane, and carbon monoxide. At Pluto's extreme temperatures, these gases freeze solid, forming vast plains of ice. And as Pluto slowly travels along its long, stretched orbit around the Sun, a single year lasting 248 Earth years, faint sunlight triggers subtle but powerful changes. Nitrogen ice doesn't melt, it sublimates, turning directly from solid ice into gas and drifting into Pluto's thin atmosphere. As seasons change and temperatures drop, the gas freezes again, settling back onto the surface like frost. This cycle happens over decades and centuries, not days or months, and over time, it reshapes the planet. Glaciers made of nitrogen ice creep across Pluto's surface, especially in low-lying regions. They move incredibly slowly, just centimeters per year. But given enough time, that motion becomes unstoppable. Frost migrates across the planet. Bright regions darken, dark regions brighten. In some areas, nitrogen ice behaves like slow-moving rock glaciers on Earth, cracking, creeping, and reshaping the terrain. Impact craters soften. Landscapes are smooth and renewed. Pluto's climate isn't driven by storms or rain. It isn't shaped by wind or rivers. It's driven by time, by chemistry, by ice that moves so slowly it feels almost frozen, yet never truly is. Pluto's climate system may be alien, but it is remarkably active. Even at the edge of the solar system, this distant world is still changing. Number 7. Sputnik Planitia, the beating heart of Pluto. The most iconic feature on Pluto isn't a mountain or a crater. It's a heart, a vast, bright, heart-shaped region etched across Pluto's surface. And the left side of that heart has a name, Sputnik Planitia. At first glance, it looks smooth and quiet, almost frozen in time. But Sputnik Planitia is anything but still. This enormous basin, roughly the size of Texas, is filled with nitrogen ice. At Pluto's extreme cold, that ice doesn't behave like rock. It behaves like a slow-moving fluid. Deep below the surface, it gently overturns in a process called convection. Warmer ice rises, cools, and sinks again. That slow churning creates the giant polygonal patterns visible from space, not impact scars, but signs of ongoing motion. The surface is constantly renewed, erasing craters almost as fast as they form. As a result, Sputnik Planitia is one of the youngest regions on Pluto, possibly less than 10 million years old. On a world more than 4 billion years old, that's extraordinary. But the real mystery lies beneath the ice. Sputnik Planitia sits almost perfectly opposite Pluto's largest moon, Charon. That alignment is too precise to ignore. One leading explanation is that Pluto may still hide a subsurface ocean, a liquid layer buried beneath its icy crust, allowing the planet to slowly reorient itself over time. If true, it means this tiny world, far beyond the sun's warmth, may still be hiding liquid water. Sputnik Planitia isn't just a surface feature. It's a clue to Pluto's interior, and proof that even at the edge of the solar system, worlds can still surprise us. Number 6. Towering mountains made of water ice. When scientists first imagined Pluto, they pictured a world too small and too cold to build anything tall. A soft sphere of ice, a frozen, collapsing relic. But Pluto proved them wrong. Some of its mountains rise more than 6 kilometers above the surrounding terrain, rivaling the tallest peaks on Earth. And what makes these mountains truly astonishing isn't just their height, it's what they're made of. They aren't built from rock, they're built from water ice. At Pluto's surface, temperatures around minus 220 degrees Celsius, water ice behaves nothing like the ice we know on Earth. It becomes incredibly rigid, as hard as granite. On Pluto, water ice forms the planet's bedrock, strong enough to support towering mountain ranges. Lighter ices, like frozen nitrogen and methane, flow around these solid foundations like glaciers around stone peaks. One striking example is the Tenzing Montes, jagged, ice-built mountains rising sharply from the plains, casting long shadows across the frozen surface. Mountains like these don't form quietly. Their existence tells us Pluto's crust is thick and strong, and that powerful internal forces once pushed it upward. At some point in its past, heat and internal stress fractured the crust and lifted these icy peaks skyward. This discovery shattered the idea of Pluto as a weak, slushy ice ball. Instead, it revealed a world with structure, strength, and a surprisingly dynamic interior. Even at the edge of the solar system, Pluto built mountains that rival Earth's, not from stone, but from ice hardened by extreme cold. And once again, Pluto refused to be underestimated. Number 5. Cryovolcanoes. Some of the strangest features on Pluto don't look like mountains, and they don't look like impact craters. They look like volcanoes. But these are not volcanoes built by fire. They are built by ice. Instead of molten rock, scientists believe these structures may have erupted slushy mixtures of water, ammonia, and other frozen compounds, materials forced upward from deep inside Pluto and spread across the surface in slow, icy flows. The two most dramatic examples are Reitmann's and Picardmann's. These features are enormous, tens of kilometers wide and several kilometers tall, making them some of the largest suspected cryovolcanoes in the entire solar system. Unlike typical mountains, they have broad, rounded shapes and deep central depressions, resembling collapsed volcanic domes. And that shape is the key. If these really are cryovolcanoes, then Pluto once had, or may still have, enough internal heat to push icy material from below the crust up onto the surface. That requires energy, pressure, and a partially warm interior. For a world this small, this distant, that idea is extraordinary. Pluto was supposed to be frozen solid. Its internal engine shut down billions of years ago. Cryovolcanoes challenge that assumption completely. They suggest Pluto's interior may have stayed warm far longer than expected, possibly aided by radioactive decay or antifreeze-like chemicals mixed into subsurface layers. If confirmed, these ice volcanoes mean Pluto wasn't just shaped by slow surface processes. At times it erupted, quietly, slowly, but powerfully. Even at the edge of the solar system, Pluto may have found a way to release its hidden heat, proving once again that this tiny world refuses to follow the rules. Number 4. Pluto and Charon, a true binary world. Most moons orbit their planets like obedient companions, but Pluto and Charon are different. Charon is so large, nearly half the size of Pluto itself, that the center of gravity between them doesn't sit inside either world. It lies in empty space between them. Because of that, Pluto and Charon don't behave like a planet and its moon. They orbit each other. Locked in an endless cosmic dance, the two worlds form a true binary system, unlike anything else in the solar system. And Charon is not just a passive partner. Close-up images revealed a surface scarred by colossal canyons, some stretching for thousands of kilometers and plunging deeper than the Grand Canyon. These fractures tell a dramatic story of ancient tectonic activity when Charon's crust was stretched and torn apart. One leading explanation is astonishing. Charon may once have hidden a subsurface ocean. As that ocean slowly froze, the moon expanded, cracking its outer shell and carving the massive chasms we see today. Together, Pluto and Charon preserve the evidence of a violent beginning. Scientists believe they were born from a colossal collision billions of years ago, an impact so powerful it reshaped both worlds and left them forever bound together. Pluto and Charon aren't just neighbors, they are partners. Two worlds locked together since the dawn of the solar system, telling a shared story of chaos, transformation, and survival at the edge of the sun's reach. Number 3. Pluto's smaller moons are chaotic. Beyond Charon, Pluto is surrounded by 4 much smaller moons: Styx, Nix, Kerberos, and Hydra. At first glance, they look like ordinary satellites. They're anything but. Unlike most moons in the solar system, these worlds don't rotate smoothly. They don't keep one face turned toward their planet. Instead, they tumble chaotically, spinning and flipping in unpredictable ways as they travel through space. The reason lies at the heart of the Pluto system itself. Pluto and Charon form a powerful binary pair, constantly tugging on each other. That gravitational tug-of-war creates a wildly unstable environment for any smaller moon caught in between. As a result, Styx, Nix, Kerberos, and Hydra are pulled and twisted from multiple directions at once. Their rotations change over time. Their spin axes wander. Some of them rotate so erratically that predicting their exact orientation far into the future becomes nearly impossible. This kind of motion is extremely rare. In fact, Pluto's moons represent one of the most dynamically complex systems ever observed. Despite the chaos, these moons have remained in orbit for billions of years. A delicate balance between stability and disorder. It's a cosmic paradox, a system that should tear itself apart, yet somehow holds together. Pluto's smaller moons are a reminder that even in the cold, distant reaches of the solar system, gravity can create worlds that behave in ways we never expected, spinning, tumbling, and dancing on the edge of chaos. Number 2, Pluto is a window into the early solar system. Far beyond the orbit of Neptune lies a vast, frozen frontier known as the Kuiper Belt, a disk of icy debris left behind when the planets were first forming more than 4.5 billion years ago. And within that distant region orbits Pluto. Unlike Earth, Pluto has never been reshaped by plate tectonics, raging oceans, or a thick, weather-beaten atmosphere. It hasn't been erased and rewritten over and over again. Much of its surface still preserves the conditions of the early solar system. That makes Pluto something extraordinary, a time capsule. By studying Pluto, scientists are effectively looking back billions of years to an era when planets were still assembling, colliding, and settling into place. Its glaciers, craters, and surface chemistry record processes that once shaped every world, including our own. Every impact scar tells a story of early chaos. Every layer of ice preserves ancient chemistry. Every frozen landscape reveals how small worlds evolved when the solar system was young. Pluto helps answer some of the biggest questions in planetary science. Why did some objects grow into full-size planets while others remain small? Why did Earth become warm and alive, while worlds like Pluto stayed cold and distant? In many ways, Pluto represents a path not taken, a reminder of how easily our solar system could have turned out differently. It isn't just a distant dwarf planet, it's a surviving relic from the dawn of planets. Still orbiting, still intact, still teaching us where we came from. Number 1, Pluto is still teaching us, even from billions of miles away. When New Horizons raced past Pluto in 2015, the encounter lasted only a few hours, but the discovery didn't end there. That single flyby returned a treasure trove of data, thousands of images, measurements, and chemical readings so rich that scientists are still analyzing them today. Even now, new studies continue to reshape what we thought we knew about Pluto's surface, its atmosphere, and its hidden interior. Pluto keeps giving up secrets, slowly, and it may not be finished. Future missions are already being discussed, orbiters that could circle Pluto for years, landers that could touch its frozen surface, and explorers that would push deeper into the Kuiper Belt, surveying other ancient worlds like it. Why go back? Because Pluto changed everything. It shattered the idea that small worlds are simple. It proved that geological activity can survive in extreme cold. And it showed us that complexity doesn't disappear just because a world is distant. Pluto may be tiny by planetary standards, but its impact on science has been enormous. It forced us to rethink what makes a planet active, what makes it interesting, and what makes it worth exploring. In the end, Pluto reminds us of something far bigger than itself. Size doesn't define importance, distance doesn't erase mystery, and curiosity, the drive to look closer, to ask better questions, is what truly moves us forward. Even from billions of miles away, Pluto is still teaching us how to explore the universe. Pluto was once stripped of its title, reduced to a definition, filed away as something small, distant, expendable, but history has a habit of humbling us. Because when we finally look closely, Pluto didn't vanish into obscurity. It revealed itself, a world with moving ice and towering mountains, with a living climate and a heart that still beats, with secrets buried beneath a frozen shell, whispering of oceans, heat, and time. Pluto didn't lose importance when we changed its name. It gained meaning. It became a reminder that the universe doesn't care about our categories, only about what is. That size doesn't define significance. That distance doesn't erase complexity. And that the farther we dare to look, the more astonishing reality becomes. Out there, at the edge of the sun's reach, Pluto keeps circling in silence, carrying a record of our origins, a challenge to our assumptions, and a promise that discovery is never finished. If this journey to the frontier of our solar system moved you, like the video, subscribe, and turn on notifications so you don't miss what's next. And tell us in the comments, should Pluto still be called a planet? Because the debate isn't really about a name. It's about how much we're willing to question and how far we're willing to explore. Thanks for watching, Orbit Crew. We'll see you on the next mission.